Quantum physics describes nature at atomic and subatomic scales, such as electrons, photons, and atoms. When we peer into the smallest realms of existence, we find ourselves in a world that operates by rules entirely different from those we observe in our everyday lives. At these incredibly tiny scales, matter and energy behave in ways that seem almost magical, yet they follow precise mathematical laws that govern everything from the glow of distant stars to the chemical reactions happening within our own bodies at this very moment. The particles that make up all the matter we see around us, the light that illuminates our world, and the forces that hold atoms together all follow the principles of quantum physics. This is not some abstract theory disconnected from reality, but rather the most fundamental description we have of how the universe actually works at its deepest level. The term quantum refers to discrete packets of energy rather than continuous values. Imagine pouring water from a container, and the flow appears smooth and uninterrupted. In the world we experience with our senses, energy seems to flow this way, continuously and infinitely divisible. But at the quantum scale, energy doesn't flow smoothly at all. Instead, it comes in specific, indivisible chunks, like coins in specific denominations rather than an infinitely divisible stream of value. These discrete packets, or quanta, represent the smallest possible units of energy that can exist for any given phenomenon. You cannot have half a quantum, just as you cannot have half a photon. This discreteness is fundamental to the fabric of reality itself, not just a limitation of our measurement tools. The universe, at its most basic level, is granular rather than smooth, digital rather than analog in a sense, though this comparison only goes so far. This quantum nature of energy has profound implications for everything that exists. Classical physics fails to explain atomic stability, radiation, and microscopic behavior. For centuries, the physics developed by Newton and Maxwell worked beautifully to describe the motion of planets, the behavior of machines, and the propagation of light and electromagnetic waves. But when scientists at the turn of the 20th century tried to apply these classical laws to atoms and the radiation they emit, they encountered profound contradictions. According to classical electromagnetic theory, an electron orbiting an atomic nucleus should constantly radiate energy as it accelerates in its curved path, just as radio transmitters emit electromagnetic waves from accelerating charges. This radiation should cause the electron to lose energy continuously, spiraling into the nucleus in a tiny fraction of a second. Yet atoms are stable. They don't collapse. Matter exists. Classical physics also predicted that heated objects should radiate infinite amounts of energy at high frequencies, an absurdity known as the ultraviolet catastrophe. These failures weren't minor discrepancies that could be smoothed over with small adjustments. They were fundamental breakdowns that revealed classical physics, for all its successes, was incomplete. Something entirely new was needed to understand the atomic world. Max Planck introduced energy quanta in 1900 to explain blackbody radiation. When objects are heated, they glow, emitting light whose color depends on temperature. A blackbody is an idealized object that absorbs all radiation falling on it and emits radiation based purely on its temperature. Planck was trying to derive a formula that matched experimental measurements of this radiation across all wavelengths. The classical approaches kept producing nonsensical results, including that prediction of infinite energy at short wavelengths. In what Planck himself later called an act of desperation, he made a radical assumption. Perhaps the energy of electromagnetic oscillators in the walls of a heated cavity could only take on certain discrete values, rather than any value whatsoever. He proposed that energy came in packets, with each packet having an energy equal to the frequency of oscillation multiplied by a new fundamental constant, now called Planck's constant. This assumption, seemingly arbitrary but mathematically necessary to fit the data, worked perfectly. The formula Planck derived matched observations with remarkable precision. Yet even Planck didn't initially realize the full implications of his quantum hypothesis. He thought of it as a mathematical trick, a useful fiction. It would take Einstein to recognize that energy quantization was a deep physical reality. Albert Einstein proposed light quanta to explain the photoelectric effect. When light shines on certain metals, electrons are ejected from the surface. This photoelectric effect had been observed, but its details contradicted classical wave theory of light. According to classical physics, increasing the intensity of light should give electrons more energy. But experiments showed that electron energy depended only on the color or frequency of the light, not its brightness. Dim violet light ejected energetic electrons, while bright red light, despite carrying more total energy, might not eject electrons at all. In 1905, Einstein proposed a bold explanation. Light itself comes in discrete packets, particles of electromagnetic energy he called light quanta, later known as photons. Each photon carries an energy determined by its frequency, using the same relationship Planck had discovered. When a photon strikes an electron, it transfers all its energy in a single quantum event. If that energy exceeds a threshold determined by the metal's properties, the electron escapes. Brighter light means more photons, producing more electrons, but not more energetic ones. This particle view of light seemed to contradict a century of evidence that light was a wave. Einstein's explanation was controversial, but it was correct, and it earned him the Nobel Prize. The quantum revolution was truly beginning. Louis de Broglie suggested that matter itself has wave properties. If light, long understood as a wave, could behave as particles, then perhaps the reverse was also true. Perhaps matter, which everyone knew consisted of particles, might also exhibit wave properties. In 1924, de Broglie proposed this symmetry in his doctoral thesis. He suggested that all matter, from electrons to baseballs, has an associated wavelength inversely proportional to its momentum. For large objects like baseballs, this wavelength would be incomprehensibly tiny, far too small to detect or produce observable wave effects. But for electrons and other subatomic particles, the wavelengths could be comparable to atomic dimensions. De Broglie's proposal was speculative, based on aesthetic and theoretical considerations, a kind of intellectual symmetry. Einstein admired the thesis, lending it credibility, but direct experimental evidence would be needed. The idea that solid, tangible matter could somehow be wave-like seemed almost mystical. Yet within a few years, experiments would confirm that electrons do indeed produce wave interference patterns, behaviors impossible for classical particles. Matter waves were real. The distinction between particles and waves, so clear and absolute in classical physics, was dissolving. The quantum world was revealing itself as something fundamentally unified yet profoundly strange. Electron diffraction experiments confirmed matter waves. When waves pass through openings or around obstacles comparable to their wavelength, they diffract, spreading out and producing characteristic interference patterns with alternating bright and dark regions where waves reinforce or cancel. This is easily observed with water waves and light waves. If electrons were simply tiny particles following definite trajectories, Firing them at a crystal or through slits should produce a pattern corresponding to the geometry of the openings, perhaps with some scattering but no interference. In 1927, Clinton Davison and Lester Germer in the United States, and independently George Thomson in Scotland, performed experiments that sent electrons at crystalline materials. The reflected or transmitted electrons produced patterns with peaks and troughs in intensity, exactly the interference patterns expected from waves. The spacing of these patterns corresponded to wavelengths matching de Broglie's formula. Matter waves were not a metaphor or a calculational convenience. Electrons were genuinely exhibiting wave behavior. Particles were waves. Or perhaps more accurately, the very concepts of particle and wave were inadequate to describe what quantum objects actually are. This experimental confirmation was revolutionary, fundamentally altering our understanding of the nature of matter itself. The wave properties of matter would become central to the new quantum mechanics being developed. Quantum mechanics explains why atoms are stable rather than collapsing. Remember that classical physics predicted atoms should be unstable, with electrons radiating away their energy and spiraling into the nucleus. Quantum mechanics resolved this crisis. When we treat electrons not as particles following definite orbits, but as wave phenomena described by wave functions, something remarkable happens. Just as waves on a string can only vibrate in certain patterns, certain standing wave modes, electron waves in an atom can only exist in certain configurations. These allowed configurations correspond to specific energy levels. The lowest energy level, the ground state, represents a stable configuration that cannot decay further because there is no lower energy state available. The electron cannot gradually lose energy and spiral inward because there are no allowed states with less energy than the ground state. It's as if the electron sits at the bottom of a staircase with discrete steps. It cannot descend further because there are no more steps below. This quantization of energy levels, arising naturally from the wave nature of matter and the mathematical structure of quantum mechanics, explains atomic stability. It explains why matter is solid and persistent. Without quantum mechanics, we literally wouldn't exist, because atoms themselves wouldn't exist in any stable form. Energy levels in atoms are quantized. An electron bound to an atom cannot possess just any amount of energy. Instead, only certain specific energy values are permitted. These allowed energies form a discrete spectrum, like the rungs of a ladder rather than a continuous ramp. Each atom, depending on the number of protons in its nucleus and thus its identity as a specific element, has its own unique pattern of allowed energy levels. Electrons occupy these levels, and the chemical properties of elements, the way they bond and interact, depend crucially on these quantized energy structures. When an electron transitions between two allowed energy levels, it must absorb or emit energy equal to the precise difference between those levels. It cannot absorb or emit arbitrary amounts. If an electron jumps to a higher energy level, it must absorb exactly the right amount of energy, often carried by a photon. When it drops to a lower level, it emits a photon carrying exactly that energy difference. This is why atoms emit and absorb light at characteristic wavelengths, producing the spectral lines that serve as fingerprints for identifying elements, whether in a laboratory sample or in the atmosphere of a distant star. The quantization of atomic energy levels is both a consequence and a confirmation of quantum mechanics, connecting the abstract mathematics to observable phenomena. Photons carry energy proportional to their frequency. Light comes in many colors, many wavelengths, spanning from radio waves through visible light to X-rays and beyond. Each color corresponds to a specific frequency, the number of wave oscillations per second. In the quantum view, light consists of photons, and each photon carries a specific quantum of energy determined by its frequency. Higher frequency means more energy per photon. A photon of violet light carries more energy than a photon of red light. An X-ray photon carries far more energy than a visible light photon. This relationship between energy and frequency, expressed mathematically by Planck's constant, is fundamental. It connects the wave properties of light, characterized by frequency and wavelength, with the particle properties, characterized by energy and momentum. This connection is what Einstein used to explain the photoelectric effect. It's why ultraviolet light can cause sunburns and damage DNA while visible light generally cannot, even though both are electromagnetic radiation. The higher frequency ultraviolet photons carry enough energy per quantum to break chemical bonds. This energy-frequency relationship is absolutely central to understanding how light interacts with matter, how solar panels convert sunlight to electricity, how our eyes detect color, and countless other phenomena. It embodies the quantum nature of electromagnetic radiation. Wave-particle duality means quantum objects behave as waves or particles depending on measurement. This might be the most perplexing aspect of quantum mechanics. Electrons, photons, atoms, and all quantum objects exhibit both wave-like and particle-like properties, but not simultaneously in the same experiment. When we perform experiments designed to observe wave properties, such as interference and diffraction, quantum objects behave as waves. When we perform experiments designed to observe particle properties, such as localized detection events, the same objects behave as particles. Which aspect manifests depends on the experimental arrangement, on what kind of measurement we perform. It's not that quantum objects are sometimes waves and sometimes particles. Rather, they are neither and both. They are quantum objects, entities that transcend our classical categories. Our language, evolved to describe the macroscopic world, lacks adequate terminology. We borrow words like wave and particle from classical physics, but quantum objects are fundamentally different from both. The duality is in our description, not necessarily in the objects themselves. This realization forces us to abandon the notion that quantum objects have definite properties independent of observation. The universe at the quantum level is far more subtle and interconnected than our everyday experience suggests. What we observe depends on how we choose to look. Quantum states are represented by wave functions. To describe a quantum system mathematically, we use a wave function, typically denoted by the Greek letter psi. The wave function is a mathematical object, often a complex-valued function of position and time, that encodes all the information that can be known about a quantum system. For a single particle, the wave function depends on spatial coordinates and time. For multiple particles, it depends on all their coordinates. The wave function is not itself a physical wave in ordinary space. Rather, it's an abstract mathematical entity that lives in a more abstract space. Its physical interpretation comes through the Born rule, which we'll discuss shortly. The wave function describes quantum superpositions, configurations where the system is in multiple classical states simultaneously. When we know the wave function, we can calculate the probability of different measurement outcomes and predict how the system evolves. The wave function captures everything quantum mechanics has to say about a system. It contains all the quantum information. Yet the wave function itself is never directly observed. We observe particles, measurement outcomes, definite results. The wave function is the hidden mathematical structure underlying those observations. It's the fundamental object in quantum theory, the carrier of quantum reality, yet it remains mysterious in its ultimate nature. Physicists still debate what the wave function really represents, whether it's a description of reality itself or merely our knowledge. The Schrödinger equation governs how wave functions evolve. Once we have the wave function describing a quantum system at some initial time, how does it change as time passes? The answer is given by the Schrödinger equation, one of the central equations of quantum mechanics. Erwin Schrödinger formulated this equation in 1926, and it has been astonishingly successful in predicting quantum behavior. The equation is deterministic. Given the wave function at one moment and the physical circumstances, meaning the forces and potentials acting on the system, the Schrödinger equation tells us exactly what the wave function will be at any future time. In this sense, quantum mechanics is as deterministic as classical mechanics. The evolution of the wave function follows precise mathematical laws with no randomness. The equation can be solved to find energy levels in atoms, to describe how particles tunnel through barriers, to predict molecular structures, and much more. It works for single particles and for systems of many particles. Schrödinger's equation is elegant, powerful, and fundamental. Yet here's the puzzle. While the equation itself is deterministic, the outcomes of measurements performed on quantum systems are not. The wave function evolves smoothly and predictably according to Schrödinger's equation, but when we measure, we get random results. This contrast between deterministic wave function evolution and probabilistic measurement outcomes is at the heart of quantum mechanics' conceptual mysteries. Time evolution of isolated quantum systems is deterministic. If a quantum system is left alone, undisturbed and isolated from external influences, its wave function evolves according to the Schrödinger equation in a completely deterministic fashion. There is no randomness, no unpredictability in this evolution. Given perfect knowledge of the wave function at one moment, we can calculate with perfect precision what the wave function will be at any later time, just as Newton's laws allowed us to predict planetary positions. The wave function might describe superpositions, bizarre combinations of states that seem paradoxical from a classical perspective, but its evolution through time is perfectly lawful and calculable. This deterministic evolution is called unitary evolution, and it has special mathematical properties, including reversibility. If we know the wave function now, we can calculate what it was in the past just as precisely as we can predict the future. Information is preserved. Nothing is lost in unitary evolution. The universe, viewed through the lens of the Schrödinger equation, is a vast, perfectly choreographed quantum dance, with every particle's wave function evolving in lockstep with every other according to exact mathematical laws. This deterministic picture is elegant and reassuring, but it makes the apparent randomness of measurement all the more puzzling. Measurement outcomes themselves are probabilistic. Despite the deterministic evolution of wave functions, when we actually perform a measurement on a quantum system, we cannot generally predict with certainty what result we will obtain. If an electron's wave function describes a superposition of being in multiple locations, and we measure its position, we will find it at one specific location, but quantum mechanics can only provide probabilities for each possible location. We might repeat the exact same experiment many times, preparing the system identically each time, and get different results. This randomness is not due to hidden variables or incomplete knowledge, as in classical statistical mechanics where we use probabilities because we don't know the exact positions and velocities of every molecule. Quantum randomness appears to be fundamental. The probabilistic nature of measurement outcomes is built into the structure of quantum mechanics itself. Einstein famously resisted this idea, believing that God does not play dice, that the apparent randomness must arise from some deeper deterministic reality we haven't yet discovered. But decades of theoretical work and experiments, including tests of Bell's inequalities, have confirmed that quantum randomness is real and irreducible. The universe is genuinely probabilistic at its foundation. This has profound philosophical implications. It means that perfect prediction is impossible in principle, not just in practice. The Born rule connects wave functions to probabilities. The wave function itself is a complex-valued mathematical function. How do we extract physical predictions from it? The answer was provided by Max Born in 1926. The Born rule states that the probability of finding a particle at a particular location when we measure its position is given by the squared magnitude of the wave function at that location. If the wave function has a large magnitude at some point, the particle is likely to be found there. If the wave function is small or zero somewhere, the particle is unlikely or impossible to find there. More generally, for any measurable quantity, the Born rule tells us how to calculate probabilities for different measurement outcomes from the wave function. This rule is fundamental but mysterious. Why squaring? Why does this particular mathematical operation give probabilities? There's no deeper derivation within standard quantum mechanics. The Born rule is a postulate, an axiom that works. It has been tested in countless experiments and never found wanting. Every quantum prediction that has been verified relies on the Born rule. Yet its origin remains somewhat mysterious. Some interpretations of quantum mechanics try to derive the Born rule from other principles, while others take it as fundamental. Regardless, it's the bridge between the abstract mathematics of wave functions and the concrete reality of experimental outcomes. Without the Born rule, quantum mechanics would be pure mathematics with no connection to observation. Many outcomes are fundamentally random, not just unknown. In classical physics, when we say something is random or uncertain, we typically mean we lack information. If we knew every detail about a coin flip, the exact force applied, air currents, the coin's precise shape, we could predict the outcome. The apparent randomness reflects our ignorance, not anything fundamental about reality. Quantum mechanics is different. The randomness in quantum measurement outcomes is not due to ignorance. We can know everything quantum mechanics allows us to know about a system, have a complete description through the wave function, and still be unable to predict measurement results with certainty. Before measurement, the particle doesn't secretly have a definite position that we simply don't know. According to standard quantum mechanics, it genuinely doesn't have a definite position. The property comes into being only upon measurement. This is not a matter of disturbance or our measurement apparatus being too crude. It's fundamental to how reality works. Einstein, Podolsky, and Rosen challenged this in 1935, arguing that quantum mechanics must be incomplete, that hidden variables must determine outcomes. But Bell's theorem and subsequent experiments have shown that if such hidden variables exist, they must have non-local properties even stranger than the standard quantum picture. The simplest explanation remains that quantum randomness is fundamental. Nature is inherently probabilistic. This represents a radical break from the deterministic worldview that dominated physics for centuries. Measuring a quantum system disturbs it. In classical physics, we can, in principle, measure something without affecting it. We might observe a planet's position and velocity with light so faint it imparts negligible momentum. But in quantum mechanics, measurement necessarily disturbs the system being measured. This isn't merely a practical limitation of our instruments. It's a fundamental feature of quantum reality. The act of measurement forces a quantum system to assume definite values for the measured property. Before measurement, the system exists in a superposition, a combination of multiple possible states. Measurement collapses or resolves this superposition into one definite outcome. This process is irreversible and uncontrollable. Once measured, the system is no longer in its original quantum state. The disturbance is fundamental because measurement requires interaction, and quantum interactions entangle systems together in ways that cannot be undone without leaving traces. Heisenberg's uncertainty principle quantifies one aspect of this. We cannot simultaneously know both position and momentum with arbitrary precision. Measuring position more precisely necessarily increases uncertainty in momentum. This isn't because our apparatus is clumsy. It's because position and momentum are complementary properties in quantum mechanics, related through the wave nature of matter. A well-defined position means a spread-out wave function in momentum space, and vice versa. The disturbance caused by measurement is thus built into the mathematical structure of quantum mechanics itself. Observation is not passive in the quantum world. It is an active intervention that shapes reality. Superposition allows systems to exist in multiple states simultaneously. One of the most counterintuitive aspects of quantum mechanics is superposition. A quantum system can exist in a combination of multiple classical states at the same time. An electron can be in a superposition of multiple locations. A photon can be in a superposition of different polarization states. An atom can be in a superposition of different energy levels. This isn't merely uncertainty about which state the system is in. The system is genuinely in all those states simultaneously. The wave function describing the system contains all these possibilities, weighted by probability amplitudes. When multiple quantum paths are possible, the system takes all of them at once. This leads to interference effects, where different components of the superposition can reinforce or cancel each other, producing probabilities for measurement outcomes that would be impossible if the system were definitely in just one state or another. Superposition is essential for understanding interference patterns in double-slit experiments, quantum tunneling through barriers, and the operation of quantum computers, which exploit superposition to process multiple possibilities simultaneously. The mathematics of superposition is straightforward. Any two wave functions can be added together to create a new valid wave function. But the physical interpretation challenges our intuitions about reality. How can something be in two places at once? Quantum mechanics says it can. Our everyday experience involves systems with so many particles that superpositions become effectively impossible to observe. But at the quantum level, superposition is the norm, not the exception. Measurement forces a single outcome. However, elaborate the superposition. However many states a quantum system occupies simultaneously, when we perform a measurement, we always get a single, definite result. We never observe a superposition directly. If an electron is in a superposition of being in two locations, and we measure where it is, We will find it at one location or the other, never both, never something in between. The measurement process somehow resolves the multiplicity of the superposition into a single actuality. This is sometimes called the collapse of the wave function. Before measurement, the wave function describes multiple possibilities. After measurement, it describes only the outcome that occurred. The other possibilities are gone, or at least no longer accessible. What causes this collapse? How does it happen? This is the measurement problem, one of the deepest puzzles in quantum mechanics. The Schrödinger equation doesn't describe collapse. It describes smooth, deterministic evolution. Collapse is something different, something additional. Some interpretations of quantum mechanics try to explain collapse as an illusion arising from entanglement with the environment. Others propose modifications to quantum mechanics to include objective collapse. Still others, like the many worlds interpretation, deny that collapse happens at all, suggesting instead that all outcomes occur in different branches of reality. Despite nearly a century of quantum mechanics, the transition from superposition to single outcome remains mysterious. Yet it happens every time we measure. Superposition and definite outcomes are both essential features of quantum reality, even though they seem contradictory. Understanding how they coexist remains one of the great challenges of physics. Heisenberg's uncertainty principle limits simultaneous knowledge of position and momentum. There are pairs of properties in quantum mechanics that cannot both be known with perfect precision at the same time. The most famous example involves position and momentum. The more precisely we determine where a particle is located, the less precisely we can know how fast it's moving and in what direction. The more precisely we pin down its momentum, the more uncertain its position becomes. This is not a statement about measurement disturbance, though that's related. It's not that measuring position disturbs momentum. Rather, position and momentum are complementary properties that cannot both have definite values simultaneously. A particle simply cannot have both a perfectly definite position and a perfectly definite momentum at the same time. Werner Heisenberg formulated this principle in 1927, expressing it mathematically as a fundamental limit on the product of uncertainties. If you multiply the uncertainty in position by the uncertainty in momentum, the result must always be at least as large as a certain minimum value related to Planck's constant. This isn't a technological limitation that better instruments might overcome. It's woven into the mathematical structure of quantum mechanics itself, arising from the wave nature of matter. Waves that are localized in space are necessarily spread out in wavelength, and since wavelength relates to momentum through de Broglie's relation, localization in position means spread in momentum. The uncertainty principle fundamentally limits what can be known, placing boundaries on reality itself. It tells us the universe has an irreducible fuzziness at small scales. Precision has limits. Perfect knowledge is impossible. This was deeply disturbing to physicists raised on classical determinism, but it has been confirmed countless times and is now understood as a basic feature of quantum reality. Spin is an intrinsic quantum property with discrete values. Quantum particles possess a property called spin, which has no true classical analog despite its name. Spin is not literal rotation, not particles physically spinning like tiny tops, though historically that's how it was initially conceived. Rather, spin is an intrinsic form of angular momentum, a fundamental property that particles simply have, like mass or charge. Every type of particle has a characteristic spin value. Electrons, protons, and neutrons have spin 1/2. Photons have spin 1. Some particles have spin 0, others spin 2. These values are quantized, coming only in integer or half-integer multiples of a fundamental unit. When we measure the spin of a particle along any chosen direction, we find only certain discrete values. An electron spin measured along any axis yields one of two possible results, often called spin up or spin down relative to that axis. We can never measure a value in between. The particle spin along that direction takes one discrete value or the other. Yet before measurement, the electron can exist in a superposition of spin states. Spin is crucial to the structure of matter. It determines whether particles are bosons or fermions, a distinction that governs their statistical behavior and whether they can occupy the same quantum state. Spin is responsible for magnetism in materials. It plays a role in nuclear magnetic resonance and MRI technology. Despite having no classical counterpart, spin is as real and fundamental as any property in physics. The Stern-Gerlach experiment revealed quantized spin. In 1922, Otto Stern and Walther Gerlach performed an experiment that provided direct evidence for quantum properties of atoms. They sent a beam of silver atoms through an inhomogeneous magnetic field, a field that varies in strength across space. Classically, if atoms had magnetic moments pointing in random directions, the beam should spread into a continuous distribution as atoms with different orientations deflect by different amounts. But that's not what happened. Instead, the beam split into two discrete spots. The atoms deflected into two distinct paths, as if their magnetic moments could only point in two specific directions relative to the magnetic field. This was direct evidence that angular momentum, specifically the spin angular momentum of electrons in the atoms, is quantized. The atoms couldn't have any arbitrary orientation of their magnetic moments. Only discrete orientations were allowed. When they measured the component of angular momentum along the direction of the field gradient, only two values appeared. This experiment demonstrated that quantum properties like spin are not just theoretical constructs but produce observable, discrete effects. It was one of the early confirmations that the quantum world truly operates differently from the classical world. The Stern-Gerlach experiment has since become a cornerstone demonstration in quantum mechanics, illustrating superposition, measurement, and the quantization of angular momentum. It reveals that even something as seemingly simple as the orientation of a particle in space is quantized, discretized into specific allowed values rather than varying continuously. Identical particles follow quantum statistics. When we have multiple indistinguishable particles in quantum mechanics, something remarkable happens that has no classical parallel. In classical physics, particles can always be distinguished in principle, even if they're identical in all properties, because we can track their trajectories. We can paint imaginary labels on them and follow them through time. In quantum mechanics, this is impossible. Identical quantum particles are truly indistinguishable. There is no way, even in principle, to tell one electron from another, one photon from another. They don't have individual identities that persist through time. The wave function for a system of multiple identical particles must reflect this indistinguishability. When we swap two identical particles, either the wave function remains unchanged or it changes only by an overall sign, becoming its negative. These two possibilities lead to two fundamentally different types of quantum statistics, two different ways that identical particles behave when multiple particles occupy the same system. Which type applies depends on the particle's spin. This connection between spin and statistics is a deep result of quantum field theory. The behavior of collections of identical particles, whether we're talking about photons in a laser, electrons in a metal, atoms in a gas, or any other ensemble, depends critically on which quantum statistics they obey. This has profound consequences for everything from the structure of matter to the behavior of stars to the possibility of technologies like lasers and superconductors. Quantum statistics is one of the most important and uniquely quantum phenomena in all of physics. Bosons obey Bose-Einstein statistics. Particles with integer spin, including photons, certain atoms, and composite particles like helium-4 atoms, are called bosons, named after Indian physicist Sachendra Nath Bose. Bosons follow Bose-Einstein statistics, which means multiple bosons can occupy the same quantum state simultaneously. There's no limit. You can put as many bosons as you like into the exact same state. In fact, bosons exhibit a tendency to cluster together in the same state, a phenomenon with no classical analog. When one boson occupies a state, it becomes easier for additional bosons to enter that same state. This leads to remarkable collective behaviors. At very low temperatures, bosons can undergo Bose-Einstein condensation, where a macroscopic number of particles all occupy the same quantum ground state, creating a new state of matter where quantum effects become visible on large scales. Superfluidity in helium-4 arises from Bose-Einstein statistics. Lasers work because photons, being bosons, preferentially emit into the same electromagnetic mode that already contains photons, leading to coherent light amplification. The properties of electromagnetic radiation, the statistics of photons, are determined by Bose-Einstein statistics. This is why thermal radiation has the spectral distribution it does, why Planck's blackbody formula takes its particular mathematical form. The tendency of bosons to bunch together, to occupy the same states, is fundamental to many of the most interesting quantum phenomena we observe. It allows quantum behavior to scale up from individual particles to macroscopic systems, creating observable quantum effects in the everyday world. Fermions obey Fermi-Dirac statistics. Particles with half-integer spin, including electrons, protons, neutrons, and quarks, are called fermions, named after Enrico Fermi. Fermions follow Fermi-Dirac statistics, which have radically different implications than Bose-Einstein statistics. The key principle governing fermions is the Pauli exclusion principle, formulated by Wolfgang Pauli. No two identical fermions can occupy the same quantum state simultaneously. Each quantum state can hold at most one fermion of a given type. If one electron occupies a particular state, defined by its position, momentum, and spin, no other electron can occupy that exact same state. This exclusion principle is responsible for the structure of the periodic table of elements. As you add electrons to an atom, they must occupy higher and higher energy levels because the lower ones are already filled. This determines the atom's chemical properties and its size. The exclusion principle is also what keeps matter from collapsing under its own gravity. In a white dwarf star, gravity is balanced by electron degeneracy pressure, a pressure arising solely from the refusal of electrons to occupy the same state. In a neutron star, it's neutron degeneracy pressure. Without the Pauli exclusion principle, all the electrons in an atom would collapse into the lowest energy state, chemistry would be impossible, and matter as we know it would not exist. Fermions are the building blocks of matter, while bosons often mediate the forces between them. This division of the particle world into fermions and bosons, based on their spin and statistics, is one of the most profound insights of quantum mechanics. Quantum entanglement links particles across distances. Entanglement is perhaps the most famous and mysterious of all quantum phenomena. When two or more particles interact in a certain way, they can become entangled, meaning their quantum states are no longer independent but are described by a single, joint wave function. In an entangled state, the properties of the individual particles are not determined, but correlations between them are perfectly fixed. If you measure a property of one particle, you immediately know what a measurement of that same property on the other particle will yield, no matter how far apart they are. This correlation appears instantaneously, faster than the speed of light. Einstein called this spooky action at a distance and thought it must mean quantum mechanics was incomplete. However, experiments have consistently confirmed that entanglement is real and that it doesn't allow for faster-than-light communication of information, thus preserving causality. The correlation is not about sending a signal, it's a fundamental feature of the joint quantum system. Entanglement is a key resource for quantum technologies, including quantum computing, quantum cryptography, and quantum teleportation. It represents a level of interconnectedness in the universe that has no classical counterpart. Entangled particles behave as a single entity, regardless of the distance between them, revealing that the concept of separate, localized objects is not fundamental in the quantum world. Quantum tunneling allows particles to pass through barriers. In classical physics, if a particle encounters a potential energy barrier higher than its own kinetic energy, it will be reflected back, much like a ball bouncing off a wall. It simply doesn't have enough energy to get over the barrier. But in quantum mechanics, because particles are also waves, they can tunnel through barriers that would be impassable classically. The wave function doesn't drop to zero at the barrier. It decays exponentially but can remain non-zero on the other side. This means there is a finite probability of finding the particle on the far side of the barrier. The thinner and lower the barrier, the higher the probability of tunneling. Quantum tunneling is essential for many physical processes. It explains alpha decay in radioactive nuclei, where an alpha particle tunnels out of the nucleus. It is the process that allows nuclear fusion to occur in the Sun, even though the temperatures are not quite high enough for protons to overcome their mutual electrical repulsion classically. Tunneling is also used in technology, such as in scanning tunneling microscopes that can see individual atoms and in flash memory used in computers. It is a purely quantum effect that highlights the wave nature of matter and the probabilistic character of quantum events. Without tunneling, the sun wouldn't shine, and life as we know it wouldn't exist. Tunneling enables nuclear fusion in stars. The sun and all stars shine because of nuclear fusion, the process where light atomic nuclei combine to form heavier nuclei, releasing tremendous energy. In the sun's core, hydrogen nuclei, which are just protons, fuse to eventually form helium. But there's a problem. Protons are positively charged and repel each other through the electromagnetic force. To fuse, two protons must get close enough for the strong nuclear force to bind them, a distance of about 1 femtometer, a millionth of a billionth of a meter. But the electromagnetic repulsion creates an energy barrier. For two protons to overcome this barrier classically, they would need to be moving incredibly fast, corresponding to temperatures far higher than the sun's core, which is about 15 million degrees Celsius. At the actual temperature in the sun's core, protons don't have enough energy to get over the barrier. Fusion would be impossible in a classical universe. But because of quantum mechanics, protons can tunnel through the barrier. Even though they don't have enough energy to go over, their wave nature allows them to pass through. The probability of tunneling for any single pair of protons is extremely low, but because there are so many protons in the Sun's core, enough fusion events happen to power the star. Quantum tunneling is the reason the Sun shines, providing the energy that sustains all life on Earth. It is a spectacular example of a microscopic quantum effect having macroscopic, even cosmic, consequences. Quantum field theory unifies quantum mechanics and relativity. Standard quantum mechanics, as developed in the 1920s, was non-relativistic, meaning it didn't fully account for Einstein's special relativity. It worked well for slow-moving particles but failed at high energies where particles can be created and destroyed. Quantum field theory, or QFT, was developed to address this, treating particles not as fundamental entities but as excitations of underlying fields that permeate all of space. Each type of particle has its own field: an electron field, an electromagnetic field for photons, a Higgs field, and so on. Particles are like ripples in these fields. QFT naturally incorporates special relativity and explains how particles can be created and destroyed as energy is transferred between fields. The first successful QFT was quantum electrodynamics, or QED, which describes the interaction of light and matter with incredible precision. It is one of the most accurately tested theories in the history of science. QFT provides the framework for the Standard Model of Particle Physics, which describes all known fundamental particles and 3 of the 4 fundamental forces. It is the language of modern particle physics and has led to a deeper understanding of the nature of vacuum, the origin of mass, and the early universe. By merging quantum mechanics with relativity, QFT reveals a universe of interacting fields where matter and energy are 2 sides of the same coin. The Standard Model describes all known particles except gravity. Building on the success of quantum electrodynamics, physicists developed quantum field theories for other forces. The electroweak theory unified electromagnetism with a weak nuclear force, explaining how they're different aspects of a single interaction. Quantum chromodynamics described the strong nuclear force that binds quarks into protons and neutrons and holds atomic nuclei together. These theories were combined into a single framework called the Standard Model of Particle Physics. The Standard Model catalogues all known fundamental particles, 6 types of quarks, 6 types of leptons including the electron, and the force-carrying particles like photons, W and Z bosons, and gluons, plus the Higgs boson which gives particles mass. The Standard Model describes how these particles interact through 3 of the 4 fundamental forces: electromagnetism, the weak force, and the strong force. It has been tested extensively at particle accelerators around the world. Every prediction has been confirmed, including the existence of particles predicted decades before their discovery. The Higgs boson, predicted in the 1960s, was finally discovered in 2012 at the Large Hadron Collider, completing the Standard Model. Yet the Standard Model is incomplete. It doesn't include gravity, which remains described by Einstein's general relativity, a classical not quantum theory. It doesn't explain dark matter or dark energy. It doesn't explain why parameters like particle masses have the values they do. Despite these limitations, the Standard Model represents an astonishing achievement, a quantum field theory that correctly describes the fundamental constituents of matter and their interactions over an enormous range of energies. Quantum mechanics underlies all modern particle physics. Every discovery in particle physics, every experiment at particle accelerators, every understanding of fundamental forces and particles rests on quantum mechanics. The collisions studied at places like CERN produce showers of particles whose behavior can only be understood through quantum field theory. The detectors record quantum processes, particle decays, and interactions that are inherently probabilistic and governed by the principles of quantum mechanics. Without quantum mechanics, we couldn't predict what happens when particles collide at high energy. We couldn't calculate decay rates, cross-sections, or interaction probabilities. We couldn't understand why certain particles exist and others don't. The symmetries that organize particles into families, the conservation laws that govern reactions, the subtle interferences that affect scattering amplitudes, all are quintessentially quantum. Particle physics is the study of nature at its most fundamental, and at that level, the rules are exclusively quantum mechanical. The Standard Model itself is a quantum theory, and any theory that eventually goes beyond it will also be a quantum theory. From the tiniest quark to the largest particle accelerator, the world of high-energy physics is a world defined and dominated by quantum mechanics. Quantum entanglement was debated by Bohr and Einstein. The early years of quantum mechanics were marked by intense debates between its founders over its interpretation and meaning. The most famous of these was between Niels Bohr and Albert Einstein. Bohr championed the Copenhagen interpretation, which emphasized the role of measurement and argued that quantum properties don't exist until observed. Einstein, a realist, found this unacceptable and argued that quantum mechanics must be an incomplete description of a deeper, objective reality. He famously said, "God does not play dice with the universe." The debate centered on concepts like complementarity, uncertainty, and especially entanglement. Einstein hoped to find a logical flaw in quantum mechanics or a way to restore determinism and locality. Bohr countered that the quantum world requires a new way of thinking, where we must accept that measurement and observation are fundamental. This intellectual struggle shaped the development of quantum mechanics and forced physicists to confront the profound philosophical implications of the theory. While Bohr is generally seen as the winner, as quantum mechanics has been consistently confirmed by experiment, Einstein's challenges pushed the field to clarify its foundations and led to deeper insights into entanglement and the nature of quantum reality. The Bohr-Einstein debates remain a legendary chapter in the history of science, highlighting the revolutionary and counterintuitive nature of the quantum world. The EPR paper questioned quantum completeness. In 1935, Einstein, working with Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics could not be a complete description of physical reality. The EPR paper, as it became known, presented a thought experiment involving entangled particles. They considered a pair of particles whose positions and momenta were correlated. By measuring the position of one particle, you could predict with certainty the position of the other. By measuring the momentum of one, you could predict the momentum of the other. But quantum mechanics says you cannot measure both position and momentum precisely on a single particle. EPR argued that if you could predict with certainty either the position or momentum of the second particle without disturbing it, simply by choosing what to measure on the first particle far away, then both properties must have been real and definite all along. The second particle must have possessed definite position and momentum simultaneously, even though quantum mechanics says such definite values can't coexist. Therefore, quantum mechanics must be incomplete. There must be additional variables, hidden from the quantum formalism, that specify the actual state of the particle more completely. The EPR argument was logically compelling given its assumptions. It seemed to prove that either quantum mechanics was incomplete or that influences could propagate faster than light. For decades, this remained a philosophical debate. But then John Bell found a way to test these ideas experimentally, transforming the EPR thought experiment from philosophy into science. Bell's theorem showed no local hidden variable theory can reproduce quantum predictions. In 1964, John Stuart Bell derived an inequality that any theory based on local hidden variables must satisfy. Local means that influences cannot propagate faster than light. Hidden variables means that particles have definite properties even before measurement, properties that determine measurement outcomes but are unknown to us. Bell showed that if you assume both locality and hidden variables, then certain combinations of measurement correlations on entangled particles must satisfy specific mathematical constraints, now called Bell inequalities. He then showed that quantum mechanics predicts violations of these inequalities. Quantum entanglement produces correlations stronger than any local hidden variable theory can generate. This was revolutionary. It meant the EPR argument could be tested experimentally. You could perform measurements on entangled particles, calculate the relevant correlations, and see whether they satisfy Bell inequalities or violate them as quantum mechanics predicts. If Bell inequalities are violated, then either locality or realism, the idea that properties exist independent of measurement, or both, must be abandoned. Bell's theorem turned one of the deepest philosophical questions about reality into an experimental one. It provided a clear way to distinguish between Einstein's vision of a local, realistic universe and the more radical vision of quantum mechanics. Experiments confirmed Bell inequality violations and entanglement. Starting in the 1970s and 1980s, and with increasing precision since then, physicists have performed experiments to test Bell's inequalities. The most famous of these were conducted by Alain Aspect and his colleagues, followed by many others using photons, atoms, and other quantum systems. These experiments consistently showed that Bell's inequalities are violated, exactly as quantum mechanics predicts. The correlations between entangled particles are stronger than any local hidden variable theory could allow. These results have been confirmed in loophole-free tests that rule out various alternative explanations. The conclusion is inescapable: the universe does not follow the rules of local realism. Either influences can travel faster than light, which would contradict relativity if used to send information, or particles do not have definite properties until they are measured. Most physicists interpret this as a confirmation of the non-local and probabilistic nature of quantum mechanics. Entanglement is a real, fundamental feature of the universe, not a sign of a flawed theory. These experiments not only settled a long-standing debate but also opened the door to the field of quantum information science, where entanglement is seen as a valuable resource to be harnessed for new technologies. Interpretation of quantum mechanics remains a subject of debate. While the mathematical formalism of quantum mechanics is incredibly successful at predicting results, there is no consensus on what that formalism actually means about the nature of reality. This is known as the problem of interpretation. The oldest and most widely taught is the Copenhagen interpretation, which emphasizes the role of measurement and suggests that quantum systems don't have definite properties until observed. But many other interpretations exist. The many worlds interpretation suggests that all possible outcomes of a quantum measurement actually occur, each in a different, branching universe. The pilot wave theory, or Bohmian mechanics, restores determinism by adding hidden variables that guide particles along definite paths. Objective collapse theories propose that the wave function collapses spontaneously and physically, regardless of observation. The Bayesian interpretation, or cubism, treats the wave function as a representation of an observer's subjective knowledge or beliefs. Each interpretation has its own strengths and weaknesses, and they often lead to the same experimental predictions, making it difficult to choose between them based on data alone. The existence of so many competing interpretations shows that we still don't fully understand the reality underlying quantum mechanics. It remains one of the most active and fascinating areas of research in the foundations of physics, challenging our deepest assumptions about the nature of existence. Schrödinger's cat illustrates the paradox of macroscopic superposition. To highlight the strangeness of quantum superposition, Erwin Schrödinger proposed a famous thought experiment in 1935. Imagine a cat in a sealed box with a radioactive atom, a Geiger counter, a hammer, and a vial of poison gas. If the Geiger counter detects a decay, the hammer breaks the vial, and the cat dies. According to quantum mechanics, after some time, the radioactive atom is in a superposition of having decayed and not decayed. Because the cat's fate is entangled with the atom, the cat should also be in a superposition of being both alive and dead. Only when we open the box and observe do we see one outcome or the other. Schrödinger meant this to show how absurd it is to apply quantum mechanics to macroscopic objects like cats. We never see cats that are both alive and dead. The paradox forces us to ask, where is the boundary between the quantum world and the classical world? Why don't we see superpositions in our everyday lives? The experiment remains a powerful tool for thinking about the measurement problem and the role of the observer. It has also led to the development of the theory of decoherence, which explains how interactions with the environment quickly destroy superpositions in macroscopic systems, making them appear classical. While we don't see live-dead cats, the paradox continues to inspire research into the foundations of quantum mechanics and the nature of reality. Decoherence explains loss of interference through environmental interaction. In the 1980s and 1990s, physicists developed the theory of decoherence, which partially addresses the measurement problem by explaining why we don't observe superpositions of macroscopic objects. Any real system interacts with its environment, surrounding particles, photons, air molecules, thermal radiation. These interactions entangle the system with the environment. When a quantum system becomes entangled with many environmental degrees of freedom, interference effects between different components of the superposition are suppressed. The system appears to be in one classical state or another, not a superposition. The information about the quantum phases, which is necessary for interference, gets distributed throughout the environment and becomes practically inaccessible. From the perspective of the system alone, ignoring the environment, superposition disappears. This process, called decoherence, happens extremely rapidly for macroscopic objects. A dust particle in air decoheres in less than a trillionth of a second. Schrödinger's cat would decohere essentially instantaneously due to interactions with surrounding air molecules and photons. Decoherence explains why we don't see macroscopic superpositions. The environment constantly monitors macroscopic objects, causing decoherence so fast that superpositions never build up. This is not a collapse in the sense of a physical change to the system itself. It's a loss of phase coherence due to entanglement with the environment. Decoherence explains the appearance of classical behavior and why certain properties, like position, are observed to have definite values while others fade into quantum fuzziness. Decoherence selects stable pointer states. Not all superpositions decohere at the same rate. Environmental interaction tends to preserve certain states while rapidly destroying superpositions of those states. These preferred, stable states are called pointer states. For most macroscopic objects, the pointer states are those with well-defined positions. This is why we see objects in definite locations rather than spread out superpositions. The environment effectively measures the position of the object continuously, picking out these stable states. This process is called einselection, short for environment-induced superselection. It explains why the classical world has the properties it does. Position, momentum, and other familiar classical quantities are those that are robust against decoherence. The choice of pointer states depends on the nature of the interaction between the system and the environment. Decoherence and einselection provide a bridge between the quantum and classical worlds, showing how classical reality emerges from the underlying quantum substrate. They don't solve the measurement problem entirely, as they don't explain why we see one specific outcome rather than another, but they explain why the world appears classical and why certain properties are seen as definite. This provides a physical mechanism for the emergence of the everyday world from quantum mechanics. Macroscopic objects appear classical due to rapid decoherence. The reason we don't see quantum effects like superposition or interference in our daily lives is not because quantum mechanics doesn't apply to large objects, but because decoherence happens so fast. For any object larger than a few molecules, the environment is constantly bombarding it with photons, air molecules, and other particles. Each of these interactions carries away a tiny bit of information about the object state, specifically its position. These interactions act like a continuous measurement that destroys any quantum superposition almost instantly. Even in the deepest vacuum of space, the cosmic microwave background radiation is enough to cause decoherence in macroscopic objects. The larger the object, the more interactions it has with its environment, and the faster it decoheres. This is why quantum effects are only easily seen in very small, isolated systems like individual atoms or photons in a laboratory. To see quantum behavior in larger systems, we have to cool them to near absolute zero and isolate them from the environment as much as possible. When we do this, we can see macroscopic quantum effects like superconductivity and superfluidity. But under normal conditions, the sheer number of environmental interactions ensures that the world looks and behaves classically. Decoherence is the process that hides the quantum nature of the universe from our everyday senses, creating the illusion of a solid, definite, classical reality. Quantum mechanics enables semiconductors and transistors. The electronic devices that define modern technology, computers, smartphones, all digital electronics, rely fundamentally on semiconductors, materials whose electrical properties are explained by quantum mechanics. In a semiconductor like silicon, electrons occupy energy bands separated by gaps. The highest filled band is the valence band, and the next band up is the conduction band. At room temperature, some electrons have enough thermal energy to jump to the conduction band, allowing electrical conduction. The quantization of energy levels in solids, arising from quantum mechanics and the Pauli exclusion principle, creates this band structure. By adding impurities, a process called doping, you can control the number of charge carriers and create p-type and n-type semiconductors. Combining these creates p-n junctions, which allow current to flow in only one direction. Transistors, The basic building blocks of all digital electronics are made from semiconductor junctions arranged to control current flow. A small voltage applied to the transistor's gate controls a much larger current, enabling amplification and switching. None of this would be possible without quantum mechanics. The band structure, the behavior of electrons in solids, the principles underlying semiconductor physics are all quantum mechanical. Classical physics cannot explain why materials are conductors, insulators, or semiconductors. The entire computer revolution, the information age, rests on understanding and exploiting quantum mechanics in semiconductors. Every computation, every bit of data processed, stored, or transmitted relies on quantum phenomena in semiconductor devices. Technology might look classical and macroscopic, but it's built on quantum foundations. Lasers rely on stimulated emission. A laser, which stands for light amplification by stimulated emission of radiation, is a device that produces a very intense, coherent, and monochromatic beam of light. Its operation is entirely based on quantum mechanical principles, specifically the process of stimulated emission first predicted by Einstein in 1917. In an atom, electrons can be in different energy levels. When an electron is in an excited state, it can drop to a lower state, emitting a photon. This is spontaneous emission. But if a photon of the exact right energy passes by an excited atom, it can trigger the electron to drop and emit a second photon that is identical to the first in every way. Same energy, same direction, same phase, and same polarization. This is stimulated emission. In a laser, a large number of atoms are pumped into excited states, creating a population inversion. When a few photons are emitted, they trigger a cascade of stimulated emissions, amplifying the light. The light is reflected back and forth in a cavity, further stimulating more emissions and creating a powerful, coherent beam. The coherence of laser light, where all the photons are in step, is what makes it so useful for everything from scanning barcodes to performing eye surgery to carrying data through fiber optic cables. Without the quantum understanding of energy levels and stimulated emission, lasers could never have been built. They are a direct application of the quantum nature of light and atoms. Magnetic resonance imaging uses nuclear spin. MRI is a powerful medical imaging technique that allows us to see inside the body without using ionizing radiation like X-rays. It works by exploiting the quantum property of spin in atomic nuclei, specifically hydrogen nuclei, which are abundant in water and fat in our bodies. Protons have a spin of 1/2, which means they act like tiny magnets. When a person is placed in the strong magnetic field of an MRI scanner, the nuclear spins align either with or against the field. A pulse of radio waves is then used to tilt the spins away from their alignment. When the radio pulse is turned off, the spins gradually return to their original state, emitting radio signals as they do so. The time it takes for the spins to return, and the frequency of the emitted signals, depends on the chemical environment and the type of tissue they are in. By measuring these signals from different parts of the body, a computer can construct a detailed 3D image of the internal structures. The entire process relies on the quantization of spin and the way spins interact with magnetic fields and electromagnetic radiation, both of which are fundamental quantum phenomena. MRI has revolutionized medicine, providing a safe and effective way to diagnose a wide range of conditions, and it is a prime example of how abstract quantum concepts can be turned into life-saving technologies. Quantum tunneling enables scanning tunneling microscopes. One of the most direct applications of quantum tunneling is the scanning tunneling microscope, or STM, invented in the 1980s. The STM uses an incredibly sharp metal tip, ending in a single atom, positioned just a few nanometers above a conducting surface. At this distance, electrons can quantum tunnel between the tip and the surface. When a voltage is applied, a current flows due to tunneling. The tunneling current depends exponentially on the distance between tip and surface. Moving the tip just an angstrom closer can increase the current by a factor of 10. By scanning the tip across the surface and measuring the tunneling current, or by adjusting the height to keep the current constant and recording these adjustments, the STM creates images of the surface with atomic resolution. You can literally see individual atoms. The STM was one of the first technologies that allowed direct visualization of atoms, confirming that atoms are real, definite objects, not just useful fictions. Images of atoms arranged in crystal lattices, molecules on surfaces, even manipulating individual atoms to spell words, all have been achieved with STMs. This technology, honored with a Nobel Prize, relies entirely on quantum tunneling. Without the wave nature of electrons allowing them to penetrate barriers, STMs wouldn't work. The exquisite sensitivity to distance makes STMs not just microscopes but tools for nanotechnology, for studying and manipulating matter at the atomic scale. Quantum tunneling, a purely quantum phenomenon with no classical analog, has become an essential tool in materials science and nanotechnology. Quantum mechanics underpins modern chemistry. Chemistry is fundamentally applied quantum mechanics. The structure of atoms, the way electrons fill orbitals, the shapes of molecules, and the nature of chemical bonds are all explained by quantum principles. The periodic table is organized according to how electrons occupy quantized energy levels and orbitals, governed by the Pauli exclusion principle. Chemical reactions occur when atoms share or transfer electrons, a process that involves the overlapping of electronic wave functions and the formation of molecular orbitals. The strength and length of chemical bonds, the stability of molecules, and their reactivity are all determined by the underlying quantum mechanics of the electrons. Even the colors of dyes and the behavior of enzymes are quantum mechanical. Modern computational chemistry uses the Schrödinger equation to predict the properties of new molecules and materials before they are synthesized in the lab. This has led to the development of new drugs, more efficient catalysts, and advanced materials with specific properties. Without quantum mechanics, chemistry would be a collection of empirical rules without a deep theoretical foundation. Quantum mechanics provides the unifying framework that explains why matter behaves the way it does at the molecular level, making it the bedrock of all chemical science and its applications in medicine, industry, and technology. Atomic clocks provide ultra-precise timekeeping. The most accurate clocks in the world are atomic clocks, which use the vibrations of atoms to keep time. Atoms of certain elements, like cesium or rubidium, have very precise and stable energy levels. By using microwave or laser radiation to transition electrons between these levels, we can create a frequency standard that is incredibly consistent. The official definition of a second is now based on the frequency of light absorbed and emitted by cesium atoms. Atomic clocks are so precise that they lose only 1 second every few hundred million years. This level of accuracy is essential for many modern technologies. For example, the Global Positioning System, or GPS, relies on a network of satellites each carrying several atomic clocks. By measuring the time it takes for signals from multiple satellites to reach a receiver, Your position can be calculated with meter-level precision. Even a tiny error in the clocks would lead to huge errors in position. Atomic clocks also synchronize the internet, enable high-speed communications, and are used in scientific research to test the fundamental laws of physics. The stability and precision of atomic clocks are a direct consequence of the quantized and unchanging nature of atomic energy levels, a fundamental feature of the quantum world. They represent the ultimate in precision measurement, made possible by our understanding of quantum mechanics. Superconductivity is a macroscopic quantum phenomenon. Superconductivity is a state where certain materials can conduct electricity with zero resistance when cooled below a critical temperature. This was discovered in 1911 and remained a mystery until 1957, when it was explained by BCS theory, named after its creators Bardeen, Cooper, and Schrieffer. In a superconductor, electrons form pairs called Cooper pairs. These pairs are bosons, and at low temperatures, they all condense into a single macroscopic quantum state, a Bose-Einstein condensate. Because they are all in the same state, they move coherently through the material without being scattered by impurities or vibrations, which is what causes electrical resistance. Superconductors also exhibit the Meissner effect, where they expel magnetic fields, allowing for magnetic levitation. This macroscopic quantum behavior has many applications. Powerful superconducting magnets are used in MRI machines and particle accelerators. Superconducting cables could transmit electricity without loss. Superconducting circuits are also the basis for some types of quantum computers. Superconductivity is a striking example of how quantum effects, usually confined to the microscopic world, can emerge on a large scale when many particles act together in a coherent way. It highlights the power of quantum mechanics to explain and enable extraordinary phenomena that have no classical equivalent. Quantum information treats information as a physical quantity. Information, long considered an abstract concept, something immaterial and separate from physical reality, has been recognized as fundamentally physical through quantum mechanics. Every piece of information must be encoded in the state of some physical system, and the laws of physics constrain what can be done with information. Quantum information theory studies information encoded in quantum systems, where superposition and entanglement create possibilities impossible with classical information. A classical bit is either 0 or 1, a definite state. A quantum bit, or qubit, can be in a superposition of 0 and 1 simultaneously. This isn't just uncertainty about which value it has. It genuinely occupies both states at once until measured. Multiple qubits can be entangled, creating correlations stronger than anything classical bits can have. These quantum properties enable new forms of information processing, communication, and cryptography. Quantum information theory quantifies how much information quantum states contain, how that information can be transmitted and processed, and what fundamental limits exist. It has revealed deep connections between information theory, thermodynamics, and quantum mechanics. The entropy of a black hole, the ultimate fate of information in the universe, the relationship between knowledge and physical systems, all are illuminated by quantum information theory. This field represents a shift in perspective, treating information not as something separate from physics but as a central concept, perhaps the central concept for understanding physical reality. The universe processes information, and quantum mechanics determines how. Qubits exploit superposition and entanglement. A qubit is the fundamental unit of quantum information, the quantum analog of a classical bit. While a classical bit is definitely 0 or 1, a qubit can be in a superposition of both. This means that if you have n qubits, they can represent 2 to the power of n states simultaneously. For 300 qubits, this is more states than there are atoms in the visible universe. This massive parallelism is what gives quantum computers their potential power. But qubits are more than just superpositions, they can also be entangled. When qubits are entangled, the state of one is tied to the state of the others, even when they are separated. This allows for complex correlations and operations that have no classical counterpart. Entanglement is essential for quantum algorithms and for tasks like quantum teleportation and error correction. Maintaining the delicate quantum states of qubits is the biggest challenge in building quantum computers, as they are very sensitive to noise and decoherence from their environment. Researchers are using various systems to create qubits, including trapped ions, superconducting circuits, and individual photons. The goal is to build a large-scale, fault-tolerant quantum computer that can exploit the full power of superposition and entanglement to solve problems that are impossible for even the most powerful classical supercomputers. Qubits are the building blocks of a new era of information technology, based on the fundamental principles of the quantum world. Quantum computers can solve certain problems exponentially faster. The power of quantum computers comes from their ability to use superposition and entanglement to explore many possibilities at once. While they won't be faster for every task, there are specific algorithms where they offer an enormous advantage. Schia's algorithm, for example, can factor large numbers exponentially faster than any known classical algorithm. This has huge implications for cryptography, as most modern encryption relies on the difficulty of factoring. Grover's algorithm can search unsorted databases much faster than classical computers. Quantum computers are also expected to be exceptionally good at simulating other quantum systems, such as molecules and materials. This could lead to breakthroughs in medicine, chemistry, and material science, allowing us to design new drugs and catalysts with unprecedented precision. The development of quantum computers is still in its early stages, but the potential is transformative. We are currently in the era of noisy intermediate-scale quantum, or NISQ, devices, which are not yet powerful enough to beat classical computers at useful tasks but are being used to explore the possibilities and develop the necessary software and hardware. The journey toward a full-scale quantum computer is one of the most exciting and challenging frontiers in science and technology today, promising a revolution in our ability to process information and understand the natural world. Quantum teleportation transfers quantum states via entanglement. Despite the no-cloning theorem, quantum states can be transferred from one location to another through a process called quantum teleportation, discovered theoretically in 1993 and demonstrated experimentally soon after. Teleportation requires a shared entangled pair of qubits, one held at each location. To teleport an unknown quantum state from Alice to Bob, Alice performs a joint measurement on her qubit to be teleported and her half of the entangled pair. This measurement yields classical information, 2 classical bits. Alice sends these bits to Bob through a classical channel. Based on these bits, Bob performs one of 4 simple operations on his half of the entangled pair. After this operation, Bob's qubit is in the same quantum state that Alice's original qubit was in. The original qubit state is destroyed in Alice's measurement, consistent with no cloning. Importantly, teleportation does not transfer matter or energy, and it cannot happen faster than the speed of light because the classical bits must be transmitted. What is transferred is the quantum information, the state itself. Teleportation is a key building block for quantum networks and quantum communication. It allows for the transfer of qubits between different parts of a quantum computer or between distant quantum nodes. It is a striking demonstration of the power of entanglement and the unique ways that information can be manipulated in the quantum world. Quantum cryptography offers theoretically unbreakable security. One of the most practical applications of quantum information is quantum cryptography, specifically quantum key distribution or QKD. Unlike classical cryptography, which relies on the mathematical difficulty of certain problems, QKD security is guaranteed by the laws of quantum mechanics. It allows two parties, usually called Alice and Bob, to create a shared, secret random key that can be used to encrypt and decrypt messages. The key is transmitted using quantum states, typically the polarization of single photons. According to the principles of quantum mechanics, any attempt by an eavesdropper, Eve, to measure or intercept the photons will inevitably disturb their state. This disturbance can be detected by Alice and Bob, alerting them to the presence of an eavesdropper. If the error rate is low enough, they can be sure the key is secure. QKD is already being used in some banking and government applications, and there are efforts to build global quantum networks using satellites and fiber optics. It represents the first commercially available technology that directly exploits the foundational principles of quantum mechanics to provide a level of security that is impossible with classical means. In a world where cybersecurity is increasingly important, quantum cryptography offers a provably secure way to protect our most sensitive information. The no-cloning theorem prevents copying unknown quantum states. In the classical world, we take for granted our ability to make perfect copies of information. You can copy a file, a picture, or a document as many times as you like. But in the quantum world, this is fundamentally impossible. The no-cloning theorem, proven in 1982, states that it is impossible to create an identical copy of an arbitrary, unknown quantum state. This is a direct consequence of the linearity of quantum mechanics. If you could copy a quantum state, you could use those copies to measure different properties and circumvent the uncertainty principle, or you could use them to send information faster than light using entanglement. The no-cloning theorem is a fundamental limit on our ability to manipulate quantum information. It's what makes quantum cryptography secure. An eavesdropper cannot copy the quantum key without being detected. It also means that in a quantum computer, you cannot simply copy the value of a qubit as you can with a classical bit. This has profound implications for how quantum algorithms and quantum error correction are designed. While it may seem like a limitation, the no-cloning theorem is actually a key feature that protects the unique properties of quantum information and ensures the consistency of the laws of physics. It's a reminder that information in the quantum world behaves very differently from what we're used to in our classical lives. Quantum key distribution is provably secure. The security of quantum key distribution protocols like BB84 has been proven mathematically, assuming quantum mechanics is correct. The proofs show that any attempt to gain information about the key necessarily introduces detectable errors. The amount of information an eavesdropper can gain is related to the error rate observed by the legitimate parties. If errors exceed a certain threshold, Alice and Bob abort the protocol. Below that threshold, they can perform classical post-processing, privacy amplification, to distill a shorter key about which the eavesdropper has negligible information. This security doesn't rely on assumptions about the eavesdropper's computational power or technology. Even if the eavesdropper has a quantum computer, full knowledge of the protocol, and advanced technology, they cannot break quantum key distribution without being detected, as long as the devices used by Alice and Bob meet certain basic requirements. This makes quantum key distribution a unique tool for long-term security, as it is immune to future breakthroughs in mathematics or computing. While practical implementations still face challenges like distance limits and hardware vulnerabilities, the theoretical foundation is rock solid. QKD represents a paradigm shift in security, moving from mathematical complexity to physical law. It's a testament to the power of quantum mechanics that it provides both the challenge of quantum computing and the solution of quantum cryptography. Quantum biology explores quantum effects in living systems. While quantum mechanics is usually associated with physics and chemistry, there is a growing field called quantum biology that investigates whether quantum effects play a role in biological processes. Some of the most intriguing examples include photosynthesis, where it's thought that quantum coherence may help plants transfer energy with nearly 100% efficiency. Magnetorreption, the ability of some birds to sense the Earth's magnetic field for navigation, may involve quantum entanglement in specialized proteins in their eyes. There are also suggestions that quantum tunneling may play a role in enzyme catalysis and even in the sense of smell. These ideas are controversial, as biological systems are warm and wet, environments where decoherence is expected to happen very quickly. However, it's possible that nature has evolved ways to protect or exploit quantum states for biological advantage. Quantum biology is a highly interdisciplinary field, bringing together physicists, biologists, and chemists to explore the boundaries of life and quantum mechanics. If quantum effects are indeed central to some biological functions, it would change our understanding of life itself and could lead to new bio-inspired technologies. It's a reminder that quantum mechanics may be even more pervasive than we currently realize, reaching from the smallest atoms to the most complex living organisms. Topological matter hosts protected edge states. Topological phases of matter are characterized not by local order parameters but by global properties, topological invariants, that cannot change without closing an energy gap. These phases exhibit remarkable properties, particularly protected edge states. In a topological insulator, the bulk is insulating, with an energy gap separating occupied and empty states, but the edges or surfaces conduct electricity via special states that are topologically protected. These edge states are robust against disorder and perturbations. You can't remove them without fundamentally changing the material's topology, closing the gap. The quantum Hall effect is a topological phase where edge states carry current around the sample's perimeter. In topological insulators, spin-orbit coupling creates surface states that are conducting. Time reversal symmetry protects these states, making backscattering impossible without breaking that symmetry. Topological superconductors host Majorana edge modes, exotic quasiparticles that are their own antiparticles. Topological protection arises from the system's global properties, the way electronic wave functions wind around the Brillouin zone, characterized by topological numbers like Chern numbers or winding numbers. These cannot change smoothly, requiring a phase transition. Topological phases exist in many contexts: electronic systems, photonic crystals, mechanical metamaterials, ultra-cold atoms. They offer potential applications in robust electronics, quantum computing using topologically protected qubits, and fundamental physics. Discovering and classifying topological phases is an active research frontier. The interplay between topology, symmetry, and quantum mechanics reveals that materials can be organized not just by broken symmetries but by topological structure, a paradigm shift in condensed matter physics that has revolutionized our understanding of quantum matter. Anyons exist only in 2 dimensions. In 3 dimensions, particles are either bosons or fermions, determined by their spin. Exchanging 2 identical particles either leaves the wave function unchanged for bosons or introduces a minus sign for fermions. But in 2-dimensional systems, the topology of particle exchange is different. If you move one particle around another and return to the original configuration, the path can be non-trivial, winding around the other particle. This allows for more general statistics. Particles in 2D that are neither bosons nor fermions are called anyons. When 2 identical anyons are exchanged, the wave function can be multiplied by any phase factor, not just plus or minus 1. These are called abelian anyons. Even more exotic are non-abelian anyons, where exchanging particles performs a matrix transformation on a degenerate space of quantum states. Non-abelian anyons are the basis for topological quantum computation. Their states are non-local, making them robust against local noise and decoherence. Anyons emerge as quasiparticles in certain 2D systems, most famously in the fractional quantum Hall effect. Their existence is a beautiful example of how reduced dimensionality and quantum mechanics combine to create entirely new types of particles and statistics. Detecting and manipulating anyons is a major goal in condensed matter physics, with significant implications for our understanding of quantum phases and for the development of fault-tolerant quantum computers. Topological quantum computing uses enyon braiding. Topological quantum computation is a theoretical approach to building a quantum computer that is inherently resistant to noise. Instead of using individual particles like ions or superconducting circuits as qubits, it uses the global properties of a many-body system, specifically the braiding of anyons in a 2-dimensional material. In this scheme, information is encoded in the non-local properties of the anyons, and quantum gates are performed by physically moving the anyons around each other, a process called braiding. Because the information is stored non-locally, it cannot be easily destroyed by local perturbations or decoherence from the environment. A small error in the path of an enyon doesn't change the topology of the braid, so the quantum operation remains accurate. This makes topological quantum computers naturally fault-tolerant, potentially reducing the need for complex error correction. The main challenge is finding and controlling the right materials that host non-abelian anyons, such as certain fractional quantum Hall states or topological superconductors. Companies like Microsoft are heavily investing in this approach, hoping that the inherent robustness of topological qubits will lead to a more scalable and reliable quantum computer. While it is one of the more difficult paths to quantum computing, its promise of hardware-level protection against noise makes it a compelling and active area of research. Braiding anyons performs quantum gates. The computational power of topological quantum computation comes from braiding operations. When you physically move anyons around each other in 2-dimensional space, the quantum state transforms according to the representation of the braid group. The braid group consists of all possible ways to exchange or braid particles, with composition given by performing braids sequentially. For non-abelian anyons, different braiding sequences generally don't commute. Performing braid A then braid B is different from B then A. The quantum state space of multiple anyons has dimension greater than 1, allowing quantum information to be encoded. Each braid corresponds to a unitary operator acting on this state space. By choosing sequences of braids, you can perform arbitrary single-qubit rotations and two-qubit entangling gates, the building blocks of quantum computation. For certain enyon types, braiding alone is computationally universal. For others, braiding combined with measurement can achieve universality. The topological nature means the exact trajectory of the enyons doesn't matter, only how they wind around each other. This provides a level of precision and robustness impossible with conventional qubits. Braiding is a physical realization of quantum logic gates, turning the abstract mathematics of quantum computation into the physical movement of exotic quasiparticles. It's a deep connection between topology, group theory, and quantum information, offering a unique and powerful way to process information at the quantum level. Quantum sensing reaches unprecedented precision. Quantum sensors use quantum systems to measure physical quantities with a level of precision that is far beyond what classical sensors can achieve. They exploit properties like superposition and entanglement, which are extremely sensitive to their environment. For example, atomic interferometers can measure gravity and acceleration with incredible accuracy, with applications in navigation, geophysics, and fundamental physics. Nitrogen vacancy centers in diamonds can be used to measure tiny magnetic fields at the nanometer scale, allowing for the imaging of individual molecules and the study of magnetic materials with unprecedented resolution. Quantum-enhanced imaging uses entangled photons to see through noise or to image delicate samples with very low light levels. Quantum sensors are also being developed to detect dark matter and to test the limits of general relativity. The field of quantum metrology focuses on using quantum effects to push the boundaries of measurement, potentially reaching the fundamental limits set by the laws of physics. As we learn to better control and manipulate quantum systems, quantum sensors are becoming essential tools in science, industry, and medicine, offering a new window into the world with a clarity and precision that was previously unimaginable. Scrambling describes information spread in quantum systems. Quantum scrambling refers to how localized quantum information spreads throughout a many-body system, becoming encoded non-locally through entanglement. When a quantum system evolves, especially chaotically, initially localized perturbations propagate, creating long-range correlations. Information about the initial state becomes inaccessible to local measurements, scrambled into global entanglement. Scrambling is quantified by out-of-time ordered correlators, OTOCs, which measure how operators at different times fail to commute, indicating information spread. Fast scrambling systems reach maximal entanglement rapidly, saturating quantum speed limits. Black holes are believed to be the fastest scramblers in nature, scrambling information in time logarithmic in entropy, the fastest allowed by causality and quantum mechanics. This connects to the black hole information paradox and quantum gravity. Scrambling is central to thermalization in closed quantum systems. Systems that scramble efficiently thermalize quickly, appearing to forget initial conditions as they reach a state that looks locally like a thermal equilibrium. Understanding scrambling provides insights into the dynamics of many-body quantum systems, the nature of quantum chaos, and the relationship between information, entanglement, and thermodynamics. It's an active area of research in both condensed matter physics and high-energy physics, bridging the gap between quantum information and the fundamental structure of space-time. Quantum gravity remains an unsolved challenge. One of the biggest goals in modern physics is to develop a theory of quantum gravity, a theory that unifies quantum mechanics with Einstein's general relativity. General relativity describes gravity as the curvature of space-time on a large scale, while quantum mechanics describes the behavior of matter and forces on a small scale. At the center of black holes and in the very early universe, both gravity and quantum effects are important, but our current theories don't work together. General relativity is a classical theory, while the other three fundamental forces are described by quantum field theories. Efforts to create a quantum theory of gravity, such as string theory and loop quantum gravity, have made significant progress but have yet to be confirmed by experiment. The challenge is immense, as it requires a new understanding of the nature of space, time, and matter at the most fundamental level. Solving the problem of quantum gravity would be a major milestone, potentially leading to a theory of everything that explains all the forces and particles in the universe. It is the ultimate frontier of physics, a place where our deepest theories about the world meet and where we expect to find the most profound answers about the origin and structure of the cosmos. Macroscopic quantum effects blur classical boundaries. While quantum mechanics governs the microscopic world, macroscopic quantum phenomena like superconductivity, superfluidity, Bose-Einstein condensation, and quantum Hall effects show quantum behavior at scales observable without microscopes. These phenomena involve vast numbers of particles acting coherently, described by single macroscopic wave functions. Macroscopic quantum effects challenge the notion of a sharp quantum classical boundary, suggesting quantum mechanics applies universally. Decoherence and entanglement with environments usually suppress quantum effects macroscopically, making the world appear classical. But under special conditions, isolation, low temperature, strong interactions, macroscopic quantum states survive. This raises questions about the quantum classical transition. Is there a fundamental scale where quantum mechanics stops applying, or is classicality always emergent from quantum mechanics through decoherence? Tests of macroscopic quantum superpositions push boundaries. Experiments create superpositions of larger and larger objects, molecules, nanoparticles, even proposals for viruses or mirrors. Each success confirms quantum mechanics at larger scales, narrowing the gap between the quantum and classical worlds. This suggests that the classical world is not a separate realm but a particular regime of a more fundamental quantum universe. Understanding how and why the world appears classical, despite its quantum foundations, is a key goal of modern physics, with implications for both technology and our philosophical understanding of reality. Quantum mechanics fundamentally changes our worldview. The discovery of quantum mechanics was not just a new chapter in physics, it was a radical shift in our understanding of the universe and our place in it. It replaced a world of certainty and clockwork predictability with one of probability and fundamental indeterminacy. It showed that the act of observation is not passive but an active part of reality. It revealed a level of interconnectedness through entanglement that defies classical intuition. Quantum mechanics challenges our concepts of space, time, and causality, suggesting a reality that is far more subtle and mysterious than it appears to our everyday senses. It has led to technological revolutions that have transformed society, and it continues to provide new insights into the deepest questions about the nature of existence. While it remains counterintuitive and difficult to interpret, its success in describing the physical world is unparalleled. Quantum mechanics is the most tested and verified theory in science, and it remains the bedrock of modern physics. It reminds us that there is always more to discover, that the universe is far richer and more complex than we can imagine, and that our understanding of reality is constantly evolving. As we continue to explore the quantum world, we are likely to find even more surprises, further challenging our worldview and deepening our wonder at the beauty and mystery of the cosmos. It replaces certainty with probability. Classical physics promised certainty. Given complete knowledge of initial conditions and the laws of motion, you could predict the future with absolute precision. Uncertainty arose only from incomplete knowledge, from not measuring accurately enough. It was epistemological, about what we know, not ontological, about what exists. Quantum mechanics makes probability fundamental. Even with complete knowledge of a quantum state, the wave function encoding everything quantum mechanics allows you to know, you cannot predict measurement outcomes with certainty for most observables. You can only calculate probabilities. The outcome of measuring a particle's position or an atom's energy or a photon's polarization is inherently random, not determined by any hidden variables or incomplete description. This randomness is built into the structure of nature itself. It's not that we're ignorant of determining factors. There are no determining factors. The universe is genuinely probabilistic. This was profoundly disturbing to many physicists, Einstein most famously, who believed probability reflected incomplete knowledge, not fundamental indeterminacy. But experiment after experiment confirmed quantum mechanics' probabilistic predictions and ruled out deterministic hidden variable theories that preserve locality. The universe really does play dice. Probability in quantum mechanics is not merely practical, a tool for dealing with ignorance. It's the fundamental language of nature. Events are not predetermined. Outcomes emerge probabilistically from quantum states according to precise mathematical rules, the Born rule and quantum dynamics. Certainty is replaced by probability distributions, definite outcomes by statistical ensembles, and this is not a flaw but how nature actually works. It replaces trajectories with amplitudes. Classical mechanics describes motion through trajectories, definite paths particles follow through space as functions of time. A ball thrown follows a parabola. A planet orbits the sun in an ellipse. At any moment, the object has a definite position and velocity. Quantum mechanics discards this picture. Particles do not have trajectories. Instead, they are described by probability amplitudes, complex numbers associated with different possible paths or outcomes. The magnitude squared of an amplitude gives a probability. When multiple paths are possible, we don't pick one, we add their amplitudes. This addition leads to interference, the hallmark of quantum behavior. In the double-slit experiment, an electron doesn't go through one slit or the other. Its amplitude for passing through the left slit adds to its amplitude for passing through the right slit. The resulting interference pattern is a direct consequence of this addition of amplitudes. Richard Feynman's path integral formulation makes this idea central. To find the amplitude for a particle to go from A to B, you sum over all possible paths connecting them, no matter how bizarre. Classical trajectories emerge as the paths where amplitudes add constructively, while others cancel through destructive interference. This shift from paths to amplitudes is a deep change in how we describe reality. It replaces a local, deterministic description with a global, holistic one where every possibility contributes to the final outcome. The universe doesn't choose a path. It explores all paths, and what we see is the result of their collective interference. It connects everything through entanglement. In classical physics, objects are localized and independent. What happens to a particle here doesn't affect a particle there unless there's a physical force between them, and even then, the influence cannot travel faster than light. Space provides a separation that ensures independence. Quantum mechanics breaks this independence through entanglement. When systems interact, their wave functions become coupled, creating a single unified state. Measurements on one part of the system instantly correlate with measurements on other parts, regardless of the distance between them. This is not because of a signal traveling between them, but because they are parts of a single, non-local quantum system. Entanglement is not rare, it's the natural result of any interaction. The universe, in its fundamental state, is a vast web of entangled systems. Our classical perception of separate, independent objects is an emergent property, a result of decoherence hiding these deep quantum correlations. Entanglement reveals a level of holistic interconnectedness that classical physics cannot capture. It means the properties of any part of the universe are ultimately tied to the state of the whole. This has profound implications for our understanding of reality, suggesting that the concept of a localized, independent object is an approximation. At its deepest level, the universe is a unified quantum system where everything is connected through the subtle and pervasive threads of entanglement. This interconnectedness is not just a theoretical curiosity, it's a real feature of the world, confirmed by experiment and essential for the future of quantum technology. It explains matter, light, and forces. Quantum mechanics is not just about strange phenomena and interpretational puzzles. It's the foundation of our understanding of the physical world. The structure of atoms, why electrons don't collapse into nuclei, why atoms have discrete energy levels, all are explained by quantum mechanics. The periodic tables organization, the basis of chemistry, arises from the Pauli exclusion principle and quantum numbers. Chemical bonding, why atoms stick together to form molecules, is quantum mechanical, involving electrons in molecular orbitals. The properties of materials, why some conduct electricity and others insulate, why some are magnetic and others not, why diamond is hard and graphite soft, all depend on quantum mechanics. Light itself is quantum. Photons are quanta of the electromagnetic field. The interaction of light with matter, the emission and absorption of light by atoms, the photoelectric effect, the operation of lasers and solar cells, all are quantum processes. Beyond matter and light, the fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force are described by quantum field theories. These theories explain how particles interact by exchanging force-carrying bosons. Quantum mechanics provides the unifying framework that connects the smallest particles to the largest structures in the universe, explaining how they are built and how they interact. It is the most comprehensive and successful description of nature we have, providing the scientific basis for almost everything we know about the physical world. It enables modern and future technology. We live in a quantum age. The technologies that define the modern world, computers, smartphones, the internet, medical imaging, lasers, would not exist without quantum mechanics. The transistor, the building block of all digital electronics, relies on the band structure of semiconductors, a purely quantum effect. Lasers, used in everything from surgery to telecommunications, are based on stimulated emission. Magnetic resonance imaging uses nuclear spin. The global positioning system depends on the precision of atomic clocks. These are the results of the first quantum revolution, where we learn to understand and exploit quantum properties of materials and light. We are now in the midst of a second quantum revolution, where we are learning to control individual quantum systems, single atoms, photons, and superconducting circuits. This is leading to new technologies: quantum computers that can solve previously impossible problems, quantum sensors with unprecedented precision, and quantum communication networks that are provably secure. These future technologies will transform society in ways we are only beginning to imagine, from designing new drugs to revolutionizing materials science to creating a secure global quantum internet. The economic and social impact of quantum technology is already immense and will only grow. Quantum mechanics is not just an abstract theory. It's the engine of technological progress, the foundation upon which the future is being built. Quantum theory continues to evolve. Quantum mechanics, formulated in the 1920s, is not static. It evolves as new phenomena are discovered, new technologies developed, and new theoretical insights emerge. Quantum field theory extended quantum mechanics to include particle creation and relativistic effects. Quantum information theory revealed information as a physical quantity and quantum computing as a new computational paradigm. Quantum thermodynamics extends thermodynamic concepts to quantum scales. Quantum gravity research seeks to unify quantum mechanics with general relativity. Topological quantum field theories describe exotic states of matter. Quantum chaos, quantum biology, quantum metrology, all are active research areas expanding quantum mechanics' reach. Experimental capabilities grow continuously. Quantum control reaches new levels of precision. Larger systems are brought into quantum regimes. New quantum materials are discovered. Quantum technologies transition from labs to applications. Foundational questions receive renewed attention with new experiments testing interpretations, exploring macroscopic quantum effects, probing the quantum classical boundary. Quantum mechanics itself might need modification. Perhaps at some scale or under some conditions, corrections to standard quantum mechanics emerge. Proposals for objective collapse, modifications to Schrödinger evolution, theories of quantum gravity, all suggest quantum mechanics as we know it might be an approximation to a deeper theory. Or perhaps quantum mechanics is exact, and the deeper theory just reinterprets it. Either way, quantum theory is not finished. It's a living, developing framework, with new chapters being written by researchers worldwide. The quantum story that began a century ago continues, with surprises likely ahead, new phenomena to discover, new technologies to develop, and new insights into reality's nature. The quantum world underlies everything we see. Beneath the familiar classical world of definite objects, positions, and properties lies the quantum world of superpositions, entanglement, and probability. This is not a separate world but the fundamental level of reality. Everything we see and touch, every atom, every molecule, every beam of light, is a quantum system, following quantum rules. The classical world we experience is an emergent phenomenon, a high-level description that arises when vast numbers of quantum particles interact and decohere. We are macroscopic beings living in a quantum universe. Our technology, our biology, the stars in the sky, all are built on quantum foundations. Understanding quantum mechanics is therefore essential for understanding the universe at its most basic level. It reveals a reality that is far richer, more interconnected, and more mysterious than it appears. It challenges our intuitions and forces us to rethink our place in the cosmos. The quantum world is not just a subject for physicists, it's the ground of all being. As we learn more about it, we gain a deeper appreciation for the elegance and complexity of nature, and a more profound sense of wonder at the universe we inhabit. The quantum world is the real world, and we are only beginning to explore its depths. Geology connects our everyday experience to the Earth's deep history. When we look around us, at the objects we use and the environments we inhabit, we are seeing the results of geological processes that have operated over billions of years. The materials that make up our world, the metals in our electronics, the stones in our buildings, the fuels that power our lives, are all products of the Earth's evolution and structure. Geology isn't just about mountains and earthquakes and the formation of continents. It's also about the coffee cup you're holding, the chair you're sitting on, the building around you, and the countless mineral-derived materials that make modern life possible. Every object is a geological specimen. Every day is a lesson in earth science, if you know how to look, if you remember to pay attention. The Earth provides everything we use, everything we touch, everything we build. We are not separate from the planet but deeply embedded in its systems, dependent on its resources, shaped by its constraints. The minerals we extract and use will eventually return to geological cycles, perhaps to be concentrated again in some future or deposit, perhaps to become part of some future civilization's technology. The atoms are conserved even as their arrangement changes. The elements persist even as they move through different forms. And in this great cycling of materials, this endless transformation and reorganization, we find both our place in nature and our connection to deep time, to the long history of the Earth and the even longer history of the cosmos. When you go about your day tomorrow, perhaps you'll see the objects around you a little differently. Perhaps you'll recognize the geological heritage in everything you touch, and perhaps that recognition will bring a quiet sense of wonder at how intimately we're woven into the fabric of the planet. The seafloor stretches beneath us as a dynamic interface, a place where geology and biology come together in an endless conversation deep below the ocean surface. It is a realm of constant change, of forces that work on scales both vast and intimate, shaping the very foundation upon which the waters rest. When we think of exploration, we often imagine distant planets or the farthest reaches of space, yet nearly 3/4 of the global seafloor remains unmapped, its geological details hidden in darkness, waiting to tell their stories to those willing to listen. The ocean floor is not a static place, not a simple basin that merely collects what falls from above. It is alive with movement, with creation and destruction happening in a grand cycle that has continued for hundreds of millions of years. At the heart of this dynamic system lies the oceanic crust itself, a layer that forms continuously at ridges while simultaneously subducting at trenches, maintaining a thickness that typically ranges from 5 to 10 kilometers. This crust is not uniform, not identical from one place to another, but it follows patterns that reveal the fundamental nature of our planet's outer shell. When we measure the oceanic crust carefully, we find it averages 6 to 7 kilometers thick, a relatively thin skin compared to the thick continental masses, and it is composed mainly of basalt and gabbro, rocks that crystallized from molten material rising from the mantle below. These rocks tell us about the Earth's internal temperature and the chemistry of the deep mantle, providing a window into the planet's interior that we could not otherwise access. In the quiet of the abyss, in the cold and pressure and darkness, the Earth's processes continue as they have for hundreds of millions of years, indifferent to whether we observe them or not, operating according to physical and chemical laws that we are still working to fully understand. The seafloor spreads, subducts, accumulates sediments, hosts life, cycles elements, stores carbon, preserves history. It is ancient and yet constantly renewing, familiar in its adherence to natural law and yet full of surprises when we look closely. It is worthy of our attention, our respect, our curiosity, and our care as we learn to explore it, to understand it, and to live in harmony with the ocean that covers most of our blue planet. The deep sea waits, patient and enduring, ready to reveal its secrets to those willing to venture into its depths, to ask questions of its rocks and sediments, to listen to the stories it has been telling for longer than humans have existed, stories of a planet alive with change, a planet where creation and destruction are two sides of the same process, a planet where everything is connected through the grand cycles of geology, chemistry, and life. Our everyday experience emerges from quantum mechanics through decoherence, environmental interaction, and statistical averaging over vast numbers of particles. But the quantum nature remains, underlying everything. When we understand that table or tree or star in full depth, we find quantum mechanics at the foundation, describing the electrons, atoms, and molecules, the light they emit and absorb, the forces holding them together. The quantum world is not elsewhere. It's here, everywhere, always. We inhabit a quantum universe. Our bodies are quantum systems, trillions of atoms obeying quantum laws, interacting quantum mechanically. The chemical reactions sustaining life are quantum processes. The light entering our eyes, allowing us to see, is carried by photons. The classical world is a veil, a high-level description convenient for macroscopic purposes but not fundamental. Quantum mechanics is the true description of reality. Recognizing this, understanding that the quantum world underlies everything we see, is both humbling and empowering. It reveals the universe as far stranger, far more subtle, far more interconnected than everyday experience suggests. And it shows that by mastering quantum mechanics, we gain power over nature at its most fundamental level, enabling us to understand, predict, and manipulate the physical world with unprecedented precision. The quantum world is the real world, and we're only beginning to fully explore its depths and harness its possibilities.